All right, so you should have watched the videos on the different types of bonds. And the next thing we need to do is learn how to name these different types of bonds. Now, for metallic bonding, there's no specified naming convention as far as chemistry goes, because we can have an extremely large number of types of bonds. I could have a mixture of 5 copper and 5 zinc. That could make a certain type of brass. And I can make a different type of brass that has very different properties, mixing 5 coppers to 1 zinc. I could throw some aluminum in there, I could throw some iron in there, I could throw some carbon in there, and all of these things would slightly change the properties, just slightly. And so because it's such a large diversity, it's impossible to have a coherent naming convention for all of these. And so instead, we have metals that just have different ratings, like 1020 carbon steel or 2020 carbon steel, things like that. So we're not going to get too deep into the metallic bonding, all right? We're going to focus more on the ionic and the covalent. Specifically, ionic bonding, we're going to focus on how to name them, because ionic compounds form a lattice structure that will have a specific ratio of atoms. Covalent bonding, we'll learn how to both name it and model it, because in covalent bonds, we can have exact, specific, discrete numbers of bonds. So I could have something like H2O. I could have 2 hydrogens and 1 oxygen making water, and every single bit of water will be one of these bonds, all by itself, hanging out with other versions of it. So if I have a cup of water, I actually just have a bunch of H2O molecules all sitting around each other. Where in ionic bonding, if I have something like table salt, which is sodium chloride, it's NaCl, it's actually going to look like, and I'm just going to partition this off here, it would look like having Na next to a Cl, next to an Na, next to a Cl, and it would have this very specific repeating pattern. There's not just one pair of NaCl sitting near other pairs of it. This sodium is attracted to this chlorine, this chlorine, this chlorine, this chlorine, and vice versa. So you get this very specific structure. And if you Google the lattice structure for any ionic compound, it'll show you a picture of what that looks like. And it's just this repeating structure over and over again that has a very specific look, that gives the compound a very specific macroscopic shape. So like on our level, sodium chloride, if you could find a crystal of sodium chloride, which I have some in the classroom somewhere, it takes on these very straight cubic structures. It's got sharp corners, and if you hit it with a hammer, it'll break along very specific faces that are almost perfectly smooth. And so that crystal structure comes because of the properties of an ionic bond. And when we have an ionic bond, we're going to be able to give it a very specific name that will relate to a very specific compound. This is probably our most scientific naming convention, and we're going to use it a lot. I'm not going to just tell you the atoms that are in a compound. I'm going to give you the name of a compound, and it'll be your responsibility to know what atoms are in there. So we need to learn this naming convention. And in order to do that, we're going to look back at a periodic table that we have towards the front of our book here. The first thing we need to look at is this table. This is a table of common ions for all of the different elements. An ionic bonding is going to be combinations of these different ions. Specifically, it's going to have a cation, a positive charge, mixing with an anion, a negative charge. So looking at the cations, I want you to notice this. There are some of these. Let's highlight this in red. There's some of these that can have multiple charges. I'm just going to circle those ones right now. Okay? We're not going to worry about these ones down here. They're not really going to come up. But looking inside this box, and you should probably go ahead and put something around this box in your own table so that you can remember this point. These ions can have multiple options. Okay? So I could have a stable compound of copper, Cu+, or copper, 2+. Either one can be perfectly stable, perfectly normal, and either one could be bonded with oxygen. I could have copper oxide or copper oxide. That's an ambiguous naming structure, so it's not allowed. We can't have an ambiguous naming structure. So we're going to have a way to differentiate which charge we have for any ion that can have multiple charges. But for any ion that doesn't, that only has one stable charge, like zinc can only ever be 2+, saying zinc oxide always means zinc 2+ and oxygen 2-. So it's always there. It's always going to be the same thing. So it's not ambiguous to say zinc oxide. Okay? So that's our first rule here, is that when we have single charges, we don't do anything special. We just give it the name zinc and the name of the anion oxygen, and we replace the end of that name with "-ide". And I'm drawing backwards here, so I don't even know if I'm... Yep, there we go, "-ide". Okay, let's look back at the front page. So, that's what I mean on this table where I say if there's only one charge possible, it's just the name of the ion. So sodium for Na+, silver for Ag+, zinc for Zn2+. Anything on that table that only has one charge, that doesn't have that dividing line, anything on that table will just have that name. If it has multiple charges possible, again, you're just going to do that name, but then you're going to put in Roman numerals identifying the value of that charge. So if I've got Fe3+, I call it iron 3. If I had Fe2+, I would call it iron 2. Copper 1 means copper with a +1 charge. Copper 2 means copper with a +2 charge. Okay? So that's going to apply to any of these on the periodic table, on this ionic table, that are in that red box. Any of these will get a Roman numeral every time it's bonded to identify what charge it has. So nickel bonded with oxygen would be nickel 2 oxide. If it was the 3+, it would be nickel 3 oxide. Okay? We're going to look more at that. We're going to get plenty of practice with that. So now we need to look at our naming conventions for the anions, so the negative charges. These are going to be pretty straightforward. If it's just the normal element, like fluorine or oxygen or chlorine, all we do is replace the end of it with an "-ide". So phosphorus would become phosphide, sulfur would become sulfide, like that. That's for what we call a monatomic anion. That means that the whole negative charge, the whole anion, is just one element. Okay? We can also have what we call polyatomic anions, where the anion is actually a mixture of multiple nonmetals. So it would look like a mixture. If I look on this page again. It would look like a mixture of some of these. So I can have S with 4 oxygens, SO4, and that whole thing has a -2 charge, and we call it a sulfate. I will not expect you to just memorize those for a test. You will eventually memorize the more common ones. You'll know sulfate, chlorate, nitrate, things like that. But you'll always have a table that will tell you. And that table is on the next page right here. So let's look at this. Let's look at some of these anions. And then we'll start looking at some examples. So here I've got Cl minus. That's just a regular chlorine anion. It's monatomic. So again, chlorine becomes chloride. But when I get an oxygen on it, or 2 oxygens, or 3 or 4, all of these are stable compounds and can bond just like chlorine can. So I could have something like NaCl, and that would be sodium chloride. I could also have NaClO. That would be hypochlorite. NaClO2, that would be sodium chlorite. I could have NaClO3, sodium chlorate, so on and so forth. So I can have any one of these, and I need a name for each of these compounds because each of these compounds has distinct properties. Okay? So, that's what this naming convention looks like. And we'll come back to this. This might not be totally clear right now, but we'll come back to it. For now, what we're going to be doing is practicing naming these using the next 2 pages. So we're going to be very, very clear here. So if I look at this page, I've got this table. And each part of the table is a single cation with 2 slots underneath an anion. And so what you're going to do in this table is in the first slot, in this top slot right here, you're going to write the formula. And in the bottom slot, you're going to write the name. Okay? Now we need to talk about how to write ionic formulas. Writing ionic formulas is just going to be these atoms trying to find stability. Remember, positive and negatives attract. They want to get together. They want to merge together to neutralize their charges. They're going to get pulled together according to Coulomb's law. And so when I have a positive here and a negative here, these 2 things will bond. They'll connect. Okay? That's why sodium and chlorine hang out together. If I have a charge that is something other than 1, these things are going to need to balance out. So if I'm looking at Na plus and CO3 2 minus, what I really have here is a positive cation trying to balance out 2 negative charges. Okay? In order to balance out 2 negative charges, I need to bring 2 positive charges. Well, CO3 is always going to bring 2 negative charges together, paired up. So for sodium, Na plus, this is just a 1, to balance out those 2, it needs to bring 2 sodiums. So the way this works is this 2 right here will tell me how many sodiums do I need to bring. So this first one, plus and minus, 1 and 1, they balance out. So NaCl. We never write the 1s, that's just implied. But CO3, for that, I need to bring 2 sodiums. So it's going to be Na2CO3. CO3 is a whole molecule, all on its own, okay? It's a whole thing, all by itself. So I bring 2 sodiums, that's why I have this 2 here, to balance out the -2 charge on the CO3. All right? So when we're writing these formulas, the way we write them is if I've got something like CO3, this number right here, tells me how many of this element, of the preceding element, show up. So CO3 means that I've got carbon bonded with 3 oxygens. Okay? And that whole thing together has a -2 charge. Okay? So that 3 that I write right there means I have 3 oxygens. Right? When I have a 3, a subscript, the lower number, That's counting a number of elements. The number up top, this is a superscript. That is always a reference to the charge. So when I'm putting these formulas together, I need to keep these numbers in the right spots so that I can properly communicate what's happening. So when I have NaCl, that means that for an entire compound, if I have a pile of table salt, I know that every pair of atoms in that table salt is 1 sodium, 1 chlorine. It is a very specific ratio. If I have Na2CO3, sodium carbonate, I will have 2 sodiums for every 1 carbonate. Okay? If I model that out, I've got C with 3 O's, and I'm going to have an Na by it and another Na by it. That's the ratio I'm going to have here. So that's why we write it in the specific way that we do. We're trying to communicate the exact number of atoms here. Moving on, I've got NaOH, Na, and then OH just has a -1, so they balance out perfectly. SO4, 2 minus. In order to balance out that charge, I need to bring 2 sodiums. It's going to be Na2SO4. The next one, PO4 with a 3 minus. This is called a phosphate. This is a common one. You'll get to know it. It has a -3 charge. So how many sodiums would I need to bring in order to balance out this -3 charge? Well, since sodium only has a +1, in order to balance out those 3 negatives, I've got 3 negatives, 1, 2, 3. They're all coming together, all at once. I need to balance that out with 3 positives. And since I'm using sodium, I can only bring 1 positive per sodium. So I'm going to have 3 sodiums for every 1 PO4. Okay? So when I write this, I identify that by saying Na3PO4. Now this one is a mistake. That should actually be NO3 minus. Okay, it should look like that. It's the same on the next page too. So fix that right away. NO3 minus. Okay. So before we look at naming these, I'm going to look at something that has multiple charges. Okay? Or something that has more than a +1 charge. So let's look at calcium here. Calcium has a 2+. So when it combines with chlorine, this column is chlorine, it's going to be CaCl2 because chlorine has a -1 charge. So it's the same logic as above. I had to bring 2 sodiums to balance out the -2 charge on the carbonate. So here I need to bring 2 chlorines to balance out the +2 charge on the calcium. If I have +2 on the calcium and -2 on a carbonate, I have CaCO3 because both of these are bringing 2 charges all by themselves. So they can hang out 1 to 1. Okay? With OH, CaOH, I need to bring 2 OHs. And since OH on its own, this guy, since this is a whole molecule all on its own, the way I'm going to identify that I'm bringing 2 of it is I'm going to put it in parentheses. And then put a 2 down there. So this 2 applies to everything in the parentheses. So really for this, I have calcium, an OH, and another OH. Okay? So that's how we should read these. Notice, when I'm writing my chemical formulas, I'm not writing any charges on these because when these have bonded, they have neutralized their charges. There are times where I might have a charge on something, but that means that it is not a neutral compound overall. So we want to be very careful that we are not drawing any charges up here. I should not be drawing the positive charge here and the negative charge here. Those go away. Those are neutralized by these atoms bonding together. So let's skip ahead. Let's do calcium and phosphate. Remember, phosphate has a -3. So if my phosphate is bringing, let's just do that over here. If my phosphate is bringing -3 all in one group, and each calcium brings 2 positives all in one group, I need to figure out how many calciums do I bring and how many phosphates do I bring. Well, clearly I need to bring at least one more calcium in order to try and balance that out. But now I've got 4 to 3, so that's not going to work. So now I need to bring one more phosphate. So now I'm at 6 total negatives. 6 negatives. Here I'm at 4 positives, so I'm just going to bring one more calcium. And now I'm at 6 positives. Notice here, I have -3 on my phosphate, and I had to bring 3 calciums to balance it out. I have a +2 on my calcium, and I had to bring 2 phosphates to balance that out. That is a shortcut to being able to do this. So here I've got Ca, and I'm going to bring 3 PO4, put that in parentheses, 2. Okay? So let's draw that one more time down below so that we can really make sure that we've got a grasp on that. So I've got Ca2 plus, PO4, 3 minus. This 2 tells me how many PO4s I need to bring. And this 3 tells me how many calciums I need to bring. So when I write this out, I'm going to write Ca3 PO4 in parentheses, because I want this to apply to the entire molecule, 2. Okay? So that's how we write our chemical formulas. Next, we need to name these compounds. So if I go back up, sodium only has one possible charge, so it's going to be sodium. And chlorine just gets that "ide" at the end, sodium chloride. So what I want you to do for these is I want you to figure out the name of the cation. This one is going to be ammonium. You can find it in that chart that I showed you. Potassium, calcium, magnesium, zinc. All of these on this first page are going to have only one possible charge. So you're not going to have to worry about those Roman numerals until you get to the second page. I'm just going to tell you which ones have Roman numerals. Fe3+, each name will get a Roman numeral 3 for that iron. Cobalt 3+, each one will get Roman numeral 3. Fe2+, each one will get a Roman numeral 2. Gold 3+, each one will get 3. And vanadium, I can't even remember if vanadium gets one. That's why we keep charts. Vanadium, it does. So for each one, you'll have vanadium 5 in order to name that properly. Okay? But then all of your anions will have the same name as well. So sodium chloride, and then we'll have sodium carbonate. Notice, in my name, I don't identify that there's 2 sodiums here. That's because that's the only way that this can actually bond. There's no way for sodium and carbonate to get together unless it's 2 sodiums to 1 carbonate, unless it's this exact ratio. So this name describes this exact formula. It doesn't have any ambiguity. It's very clear. Next one is sodium hydroxide. Next one is sodium sulfate. And I can find these names by looking in this table at the front. Here it is. So I had an SO4, so I look down here, and notice these are separated by their charges. So I look down here, and I've got SO4, 2-, that's sulfate. So I just say sodium sulfate. Okay? So using this table and this table, go through write all of the formulas for both of these pages and write all of the names, okay? I will post an answer key, but this should all be filled out.